Today we will talk about using f prime of x to learn things about f of x, in particular where f of x is increasing, decreasing, and where there are local extrema. Now some language. An extremum is a maximum or a minimum, and local extrema, which we talked about last time, are also known as relative extrema. Okay, so what does the first derivative tell us? If f prime of x is bigger than 0 on an interval I, then f of x is increasing on I, which means positive slopes of tangents means the function goes up. If f prime of x is less than 0 on an interval I, then f of x is decreasing on I. Negative slopes of tangents, function is going down. Now, we can use this to figure out what sort of extrema we've got. And what we're going to use is something called the first derivative test. So suppose c is a critical number for f of x. And you remember that means it's a point in the domain of the function where the first derivative is 0 or the first derivative does not exist. And we'll assume that f of x is continuous at c and differentiable in the neighborhood of c. That means if you're close to c, the thing is differentiable. It may not be differentiable at c, but it is continuous there. If f prime changes from positive to negative across c, there's a local maximum. If f prime changes from negative to positive across c, there's a local minimum. And if f prime does not change sign across c, there is no local maximum or minimum at c. Now, one does not memorize this. One draws little charts of the first derivative that tell you exactly this. So, for example, here's a chart of f prime. Let's assume that on the left-hand side of c it's positive, and on the right-hand side of c it's negative. Positive f prime means increasing f. Negative f prime means decreasing f. If you look at this picture, that's the picture of a local maximum. Now, if it's reversed, f prime is negative on the left-hand side of c and positive on the right-hand side, then we have a decreasing f and increasing f, and that's a local minimum. Now, if we have no change in sign, positive on this side, positive on this side, the function increases and then it increases. So this function is increasing on this entire interval that's pictured. Same story here, negative, negative for f prime, then f is decreasing, decreasing, so f decreases through that entire interval. There is no local max or local min in either of these two pictures. Let's do a few quick examples. So assume f of x is x squared, f prime is 2x, and pretty obviously x equals 0 is a critical number because the derivative is 0. We draw our little chart. 2x is negative when x is negative and is positive when x is positive. That means f goes down, then up. We have a local minimum. And if you look at the graph, this is just y equals x squared. There's your local minimum at 0. Let's look at f of x equals x cubed. F prime of x is 3x squared. Again, x equals 0 is a critical number because f prime is 0. We draw a chart. This time, when x is negative, 3x squared is positive. When x is positive, 3x squared is positive. So we have this picture. F goes up and goes up. There's no local max or min here. And we can see that the graph has the typical cubic shape, and you can see 0 is a critical point. There is a horizontal tangent, but we have neither a maximum nor a minimum here. Finally, let's look at f of x equals minus x to the 2/3. Now you take the derivative, you get minus 2/3 x to the minus 1/3, which we're going to rewrite as minus 2 over 3x to the 1/3. X equals 0 is a critical number, not because the derivative is 0, but because the derivative does not exist, but you'll notice that the function is perfectly continuous at x equals 0. So this is, in fact, a critical number. We look at our little chart, okay? When x is negative, the cube root is negative. So we got negative denominator, negative here, which is positive. When x is bigger than 0, the cube root is positive, 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 negative, negative. Goes up, goes down. This is a local maximum. And here's what the graph looks like. And what you can see here is that's what a local maximum looks like. There's actually what's called a cusp here. This is a vertical tangent, that's a vertical tangent, but this is in fact a local maximum. Now let's look at a slightly more complicated function, which we will chart, and we will find out things about where it's increasing, decreasing, and the local extrema. The function we will consider is f of x equals x squared over x minus 1. We note that the function is undefined when x equals 1. So x equals 1 is not in the domain of the function. We begin by calculating the derivative of f of x, and we use the quotient rule. So f prime of x is the denominator, x minus 1, times the derivative of the numerator, 2x, minus the numerator, x squared, times the derivative of the denominator, 1, over the denominator, x minus 1 squared. We simplify the numerator, and it looks like x squared minus 2x. And then finally, we factor the numerator, and we end up with x times x minus 2 over x minus 1 squared. From here, we can read off the critical points, and they occur when x equals 0 and when x equals 2. These are places where the derivative is 0. The derivative does not exist at x equals 1. But notice that the function is not defined at x equals 1, so this is not a critical point. Now we chart the derivative, and the first thing we do is write down the three important x values, 0, 1, and 2. 0 and 2 are critical points. 1 is a place where the first derivative doesn't exist, and in fact the function does not exist. So to indicate that the function does not exist, we will draw a vertical line at x equals 1. And when we draw anything resembling the graph of the function, we will not cross this line. The next thing to do is to look at what's happening to the function in various intervals. When x is less than 0, f prime of x looks like x times x minus 2 over x minus 1 squared. X is less than 0, x minus 2 is less than 0, and x minus 1 is less than 0. So we have minus times minus over minus squared, and that's plus. So in this interval, f prime of x is positive. As a result, we indicate that by putting pluses on our chart when x is less than 0. Now we move to the next interval, which is when x is between 0 and 1. In this case, x is positive, x minus 2 is negative, and x minus 1 squared is a negative squared. So we have negative times positive over negative squared, which is negative. And we go to our chart and we put minus signs between 0 and 1. Now we move to the next interval between 1 and 2, and we do exactly the same thing. And this time, x is positive, x minus 2 is negative, x minus 1 is positive. So we've got positive times negative over positive squared, which is negative. We go to our chart and put in minus signs. And the last interval is when x is bigger than 2 And now x, x minus 2, and x minus 1 are all positive, so we have positive, positive over positive squared, which is positive, and we put pluses on our chart. Now what we do is use the information on the chart to sketch the basic shape of the graph. And we do this by drawing lines that slope upward where f prime is positive, and drawing lines that slope downward where f prime of x is negative. And it's important not to cross the line x equals 1 where the function does not exist. So what we end up doing then is sketching something that goes up between minus infinity and 0, down between 0 and 1, down between 1 and 2, and up between 2 and infinity. The next thing to do is try and figure out from here where the function is increasing and decreasing. F of x is increasing where the lines go up, and you can see that's between minus infinity and 0, and between 2 and infinity, which is where f of x is increasing. We look to see where the lines go down. That's between 0 and 1 and 1 and 2. So f of x is decreasing on 0, 1, union 1, 2. Notice that it is incorrect to say that the function is decreasing between 0 and 2 because the function is not defined at 1. So you have to break the interval so that we're only talking about places where the function is defined. Okay, now what we want to know is what sort of extrema have we got? So we look at x equals 0, and we can see that we go up to the left and down to the right, which makes it a local maximum. And then we look at x equals 2, and we see that we go down from the left and up from the right, which makes it a local minimum. Let's look at another example. This time we're given the graph of y equals f prime of x. If you have a graph of y equals f prime of x, charting the first derivative is even easier. So the first step is to find the critical numbers. Those are places where the first derivative is 0, so minus 3, minus 1, and 2 are our critical numbers. Now we make our chart. We observe that when x is less than 3, the derivative is positive, so we have pluses here. Between minus 3 and minus 1, the derivative is negative. Remember, this is the graph of the derivative. Between minus 1 and 2, positive. And between 2 and infinity, also positive. And now we draw in little lines that indicate what f is doing. Positive goes up, negative goes down, positive goes up, positive goes up. Now we look at what we've got, and we see that f of x is increasing between minus infinity and 3, and is increasing between minus 1 and infinity. Okay, 2 is a critical point, but it is not a max or a min. This function increases on that entire interval. F of x is decreasing between minus 3 and minus 1. And now if we look at the picture here, minus 3 is clearly a local maximum, minus 1 is clearly a local minimum, and 2 is a critical point that is neither a local maximum nor a local minimum.